In this video, we are discussing thermochemistry, and thermochemistry is the study of energy and heat. These are your learning targets. And you'll see that one of these actually look familiar. Q equals MCAT is one that we've done earlier this year, and we will come back to it today. So we know that matter has a capability of changing from one state to another. So what do I mean by states of matter? I'm talking about solid, liquid, and gas. So when we heat up a substance, and let's use water as an example, if we have ice water and we heat it up, it's going to turn into liquid water, and then it'll evaporate and turn into water gas. And we can do the opposite, right? When we cool it down, water can go from a gas to a liquid into a solid. So when we think about these three states of matter, and we think about what is going on at a molecular level, for solids, we know that there isn't a lot of space between the particles, right? And for liquids, the space in between them start to increase, and gas, they're dispersed. There's a lot of space between them. Solids don't have a lot of freedom of motion, whereas gases do. They can move anywhere and everywhere. In a solid, the attractive forces between the particles are strong, and in a gas, they're weak. When we heat up a substance, we can graph it into a heating curve. So each substance has its own unique heating curve. And on the graph, you can see on the y it has temperature, and on the x it's the heat, the amount of heat or energy that's being added or absorbed. On the heating curve, we first start out with a solid. And as we add energy, this solid will turn into liquid. Right? So what happens in between that solid to liquid state? Right, a substance starts to melt. So if you think about water again, and pretend we have ice water, and you see it starting to melt, then as it melts, what do you see in your cup? You have both ice water and liquid water, right? So at this next flat point, we have both solid and liquid states of matter. And we keep heating it up, we now have fully liquid. You keep heating it up, what's going to happen? Your liquid water starts to evaporate, right? And when it starts to evaporate, we have both liquid and gas, and eventually we'll have just all gas. So these are your states, right? And this is what we talked about before, solid, liquid, and gas. When a solid turns into a liquid, we say that it melts, and it's going through a melting phase change. And when a liquid turns into gas, we say that it's going through a vaporization phase change. These are both endothermic, meaning energy is absorbed. Energy needs to be absorbed in order for a substance to melt and in order for a substance to evaporate. If we do the opposite, if we were to cool it down, then a gas to a liquid is called condensation, and a liquid to a solid is called freezing. And these two phase changes are exothermic, meaning that energy is being released. Now this graph can also tell us other pieces of information. For example, if we look at the melting part of the heating curve where we see solid and liquid, this tells us that yes, the substance is going through a melting phase change, but this graph will also tell us the melting point. And if we look at the vaporization, that will also tell us the boiling point. So how do you read the melting point and boiling point? All you have to do is take this line and go all the way to the y, and that point right there will give you the melting point. And for boiling point, again, you take it all the way to the y, and you can read the boiling point there. And again, every substance has its own unique heating curve, and every substance has its own unique melting point and its own unique boiling point. Here we see what's happening to the energy of the particles, right? So we start off with low energy, if you look up here, and then as the substance turns into a gas, it gets higher and higher in energy. So this is just showing you just on a molecular level what is happening with the particles at each state. Now, here are some questions that I want you to consider. What is happening to the temperature during each section of the graph? So if you look at the part where it's fully solid, the slanting point, the first slant of the graph, we can see that the temperature is increasing as we add more heat. And then what happens here at the solid and liquid point? Temperature, nothing happens to the temperature. Temperature stays constant, right? Temperature, it doesn't change. And so it stays constant. And at this point, it's not that nothing is happening. Heat is still being added to our substance, right? So as heat is being added to our substance, something is happening at the molecular level, which we're going to get to in a couple of minutes. And again, at the liquid point, we see that the temperature is increasing. Here at the vaporization, we see that temperature is again constant. And at the gas state, we see that temperature is changing again. So the next two questions I want you to think about. What is kinetic energy? What do you think is happening to the kinetic energy during each section of the graph? What is potential energy? What is happening to the potential energy during each section of the graph? Now you might remember back from 8th grade, you learned these two words, kinetic energy and potential energy. You learned kinetic energy as the energy of movement, and you learned that potential energy is the energy that is stored energy. So if we look at our graph, we can see that the kinetic energy is changing when there is a temperature change. So as energy is being added to the substance, the kinetic energy also increases at sections AB, which is the slant point here, CD, right here, and EF. So then, in what sections do you think potential energy is changing? Well, it's the sections that we didn't talk about, right? So potential energy, again, is stored energy. Think of it as this is where the molecules are repositioning, okay? So as energy is added to the substance, the potential energy of the particles increase in the flat sections of our graph, B, C, and D, E, okay? So as the potential energy is changing, the molecules are repositioning, and the molecules are getting further apart. And what's going to happen as the molecules are getting further apart? Intermolecular forces are breaking, right? You guys remember intermolecular forces? Remember there's three forces: dispersion force, dipole-dipole force, and hydrogen bonding. Remember, this is the force that's holding the two or more molecules together, right? So it's not within the molecule, but it's what's holding the two molecules together, okay? So these forces need to break in order for a substance to go from a solid to a liquid or a liquid to a gas. Now the rate of temperature increase depends on the specific heat. And do you guys remember what specific heat is? Specific heat is the heat required to raise 1 gram of a substance by 1 degree Celsius. Now, do you remember when we talked about this in the beginning of the year? I had given the example of us at the beach. And at the beach, we have 3 substances: water, sand, and a piece of metal, piece of copper metal, right? And we get to the beach, and it is blazing hot outside, so we want to get to the water as fast as we can. We take off our sandals, and we're running and running and running, and we step on a hot piece of metal. Now, how does that metal feel? It feels extremely hot on the bottom of our feet, right? So we keep running. Our feet are hitting the sand, and the sand, it feels hot, probably not as hot as the piece of metal we just stepped on. And you finally reach the water, and how does the water feel? It feels cool, right? And these 3 substances, they're all different, and yet at the same location, under the same sun, they all feel so different. Because if you remember, metals have a very low specific heat capacity, meaning that it doesn't need a lot of energy to raise 1 gram of a substance by 1 degree Celsius. It absorbs heat rather quickly and it cools down rather quickly, which is why we use them as conductors, right? And then water has one of the highest specific heat capacities, meaning water needs a lot of energy in order to raise the temperature, or even vice versa, to cool it down. So here, when we look at this heating curve, we can see that where we see the slants, all right, on the heating curve. This rate of temperature increase will depend on the substance's specific heat capacity. Now, let's talk about the parts where it's flat. Okay? When we talk about the energy exchanged during the melting point, we call it the molar heat of fusion. And the molar heat of fusion is the heat required to melt 1 mole of a solid substance. When we talk about the energy exchange during the boiling point, this is called molar heat of vaporization. The molar heat of vaporization is the heat required to vaporize 1 mole of a liquid. The heat changes that occur during chemical and physical processes can be measured accurately and precisely using a calorimeter. And a calorimeter is an insulated device, kind of like what you see here. You see that these are it's a simple calorimeter with styrofoam cups and a top, and this is a stirrer and a thermometer in there, so we can measure the temperature change. Calorimeters are used to measure the amount of heat absorbed or released during a chemical or physical process. We can calculate the amount of heat lost or the amount of heat gained because of the law of conservation of energy.